In the last video, I posed a question towards the end and I'll repeat it because there might be new viewers. The question was, we know that a person sitting on top of the train, if they shout, then the speed of the train does not get added to the speed of the sound wave, that is the shout, and it just keeps traveling at the speed of sound in air plus some wind speed if there is wind. But for this lecture, we'll assume that no wind is blowing with respect to the ground. So, and my question was, yes, I know that when the train is coming, I hear it like, so I hear the frequency shift. But of course, if there is a standing train and I hear an incoming train, then the frequency, the pitch of the incoming train is higher. So I hear it a little bit higher pitch. And now my question was, what if this is just an interpretation? What if it's the same frequency, but the wave is traveling faster, and but my brain expects the sound to travel at the same speed, so it interprets it as higher frequency? Because you could have a wave at the same frequency travel faster, and you would all think that if you're assuming that the speed doesn't change, then you would infer that the frequency must be higher. But if you assume that the frequency is not changing, then you would have to infer that the speed is higher. So is it just a matter of convention? Are we missing out on something? And this is what we're going to discuss now, because it has an answer. It is not convention, it is so now imagine there is a source of sound that makes beep beep beep, 3 beeps, and it's not moving with respect to you, with respect to the board, who cares? And this is the first beep, this is the second beep, and most recent has not grown out that much, so this is the third beep. Now there's another source which is moving. So the first beep, it starts at the same location, and so the first circle of beep is at the same as this one. Then it moves here and makes another beep, and now this circle, it has shifted. The third circle is shifted even more. So you can see that if you are receiving the beeps here, then these would come at these intervals, except if you, in this case, they would come at shorter intervals. So the wavelength has reduced, or in other words, frequency has increased. You have more beeps per second, per minute, whatever, per unit of time. So it looks like this has blue shifted, and in this case, if someone is observing here, they would see that the wavelength has increased, so it's been red shifted. And this is what would happen if the speed of the wave is independent of the speed of the emitter. You have to understand this fact. And the emitter themselves would see that, oh, I emitted a wave, and it's like the first beep is over there. I emit another wave, but I'm closer to it, and the second is here and third is here, and they can also see the same geometric shape. They would not see this. So now the question is, if the speed of the emitter were added to the speed of the wave, then of course they would not think that there is a medium at all, and they would see that the first beep is over there, and the second beep is over there, and the third beep is over there. But they, because they cannot detect their speed from here, they can detect their speed um, by measuring the distances between the faces of the waves. But if their speed got added to um, the the wave, then they would see it like this. They would see it here, the second and third here. So but why? I mean, I forgot why. Let me think. Let me pause and think. Yes, I am correct. It's easier to understand if you're throwing balls. If, let us say, you are on top of a spaceship and you're throwing balls, and if the speed of the ball was added to the speed of the spaceship that you're sitting on, of course if you cannot see anything else, then you are at rest, and you throw the first ball, you throw the second ball, and you throw the third ball, and the distance in between these two balls, if they are like this, is one case. Another case is, if regardless of you throwing the ball always goes at same speed. You could throw it as hard as you want, but it's still going to go at the same speed. In that case, you throw the first ball, but then it travels at the same speed. The second ball, it travels at the same speed, and the third ball, it travels at the same speed. Then the distances between the ball would be a factor of how fast you're going in that direction. If you're going too fast, then you throw the ball and it's only like slightly ahead of you, and then you throw the second ball and then it's here, and then you throw the third ball, it's here. So the distances have really shrunk as compared to whether if the ball that you throw, you see it go at the speed that you throw it, then in that case you throw the first ball, it's going to be far ahead of you, and you have the second ball and the third ball, then the distances would be larger. So that means that since we observe a blue shift, that means that the ball that you're throwing or the wave that you're shouting travels at a constant speed regardless of at what speed you throw it. So the fact that we have blue shift and red shift means that the speed of the wave is independent of the observer. If it were adding up, then there would not be. It would be like this diagram just translating, which would look very unphysical. Now some of you might have had a question again, um, but isn't in special relativity like here you can tell your speed and uh, based on what the redshift is, so isn't that breaking special relativity? And questions about ether and medium we'll discuss in another video. I have to go home. Bye.